Good afternoon, everybody. I'm Chaitali Shah, and I believe most of you remember me from yesterday. So, how many of you want another quiz? Raise of hands. Well, chocolates were only for yesterday. I told you, it's only a fair deal, man. Okay, fine. I will ask you all one question. If you answer it correctly, there are 3 parts in the question. All the chocolates that remain from yesterday are yours. Okay? This is the big lottery prize. This is a question that I asked you all yesterday. Now I want to see how many of you are actually paying attention. There are 3 spots blotted out. I don't want the answer to yesterday's question. I want to know the answer to all the 3 blots. All 3 plots is all the chocolates that remain from yesterday. So the question is, the well-known physicist in the image is known for his work in the path integral formulation of quantum mechanics, the theory of quantum electrodynamics, the physics of the superfluidity of supercooled liquid helium, as well as his work in particle physics. For his contributions to the development of quantum electrodynamics, he received the Nobel Prize in Physics in 1965 jointly with who? And I read out this entire thing yesterday. So I can see you like with your phones. You are disqualified, sir. So, okay, you mostly must remember what is in the blue space there. Author of the popular book? Surely you're joking, Mr. Feynman, yes. Who remembers the other 2 physicists who also got the Nobel Prize? No, it rhymes with, one of the answers kind of rhymes with Schrödinger, but is not. Yeah. Yes, one of them is Schwinger, and there's another author. Chocolates are out of the question because clearly you guys don't remember the other author, but yeah. Okay, fine, let me not keep you all waiting. Julian Schwinger and Tomonaga. These are the other 2 people who got the Nobel Prize along with Feynman. And this is a quote also that I presented yesterday. Now, another follow-up question. Can you identify these 2 people? Okay. Sure. Yes. So, yes. So on the right, we had Richard Feynman. And the next person is the speaker for the next talk, Apoorva Patel. He is a professor at the Center for High Energy Physics. He is notable for his work on quantum algorithms and the application of information theory concepts to understand the structure of genetic languages. His major field of work has been the theory of quantum chromodynamics, where he has used lattice gauge theory techniques to investigate spectral properties, phase transitions, and matrix elements. So can I have a big round of applause for him as we welcome him to the stage? So, many of you had a lot of questions for me yesterday. If you do not ask them today, I'm going to call on you, okay? So I better see a lot of participation here.
So, all right, I believe you have heard a lot of technical stuff in previous lectures. And if you had technical questions, you should have asked in those talks themselves. My job here is to answer much more fundamental questions, and that is to remove a lot of hype and resulting confusion benefit of the social media. And this is the place where you need to understand carefully what is important and what should be ignored. It is not a question of a democratic vote in the sense that 10 people have said this, that why it must be correct. No, it doesn't work that way. You have to understand the science behind the subject and make a judgment, an informed judgment about the subject and what is possible, what would you like to do, where is the field going to go, etc., etc. And that is the point of view from which I am going to answer the questions. And the first priority for the questioners is students. Okay, the other people can wait or ask me later in the session, but the immediate concern is to make students have very clear picture of what the subject is and what is important to pursue. It also comes with all kind of constraints, and my job is to help you various kind of constraints which exist, either because of our capabilities or because of our circumstances. And if you don't ask me questions, I will go home.
Yeah. My name is Jainam Patel. I'm from Christ University, currently doing my undergraduate. I'm final year student, computer science background. Just today, that session just sir handled, and they made one point that in while explaining about quantum computer, they explained that when a qubit or more than one qubits are in a superposition state, it can process parallelly all the states or multiple states at the same time. But it's not true, means it's not correct thing to define, as sir said, that what's the correct thing to define? I want to ask. Superposition means.
Okay. Okay, let me start with something much more basic than that, and that is to understand the concept of what is best labeled as quantum advantage. Okay, where will you find quantum advantage? If you don't find quantum advantage, you are not going to use all the quantum technology, even though it may be perfectly possible. So for that, it is worthwhile to go back and inspect why was quantum theory invented in the first place. It was invented because there were a lot of experimental observations which could not be explained by the existing classical theories. Could not be explained. That is the important part. It is not that the classical derivation became very long and you wanted a two-line answer to the derivation and you invented quantum theory. That is not the point. The classical theories completely failed. And so you had to invent a new sort of dynamics corresponding mathematical framework which will explain those observable phenomena. Most of the observable phenomena were at the atomic and molecular level at that time. The range has expanded a little bit after that, but still it's dominated by those phenomena. And so where will the quantum advantage come from? It will come from the possibility that your problem has those unexplained classical phenomena somewhere sitting in your problem. If it is not there in your problem, and mind you, there are lots of classical phenomena which are perfectly available and explained, like planetary motion or fluid dynamics or even electric circuits which are there in mobile phones and laptops. They were all perfectly explained by classical physics. You did not need quantum physics to explain them. And then you ask, can I get more out of the quantum physics for this phenomena? The answer is no. You need this new phenomena somehow involved in the problem you are trying to tackle. If it is not there, well, our classical devices are going to work as well as anything which can be developed using quantum physics, and then it is not a question of quantum advantage. That makes it very clear that the advantage, quantum advantage, is problem dependent. It is not universal. If you think that everything will get replaced by some quantum technology, no, it's not the case. And there is a second reason which is again very much buried in the physical world that we live in, that quantum signals are extremely fragile. You need a lot of protection from the environment to sustain those signals. They will live for some time, and then you will be able to observe the states and get some result out of it. But without that extra shielding, protection, whatever cooperative structure you will need to invent, the signal is going to disappear. And you then will not get anything, because the quantum dynamics, whatever you are trying to take advantage of, is not living long enough. And that is what makes quantum technology expensive. How do you build all that cooperative environment and protection and shielding? It's a highly non-trivial job. And unless you do that, the signal is not going to survive, and you are not going to extract anything out of it. And building that environment requires very specialized effort. It requires highly cooperative situation among every component that is involved. It is not that you leave it out in the open, it will do the job. It's not going to happen that way, and it makes it expensive. So now you have a second point, that the quantum phenomena which we encounter in nature are highly fragile, while we know that the classical phenomena are very robust. They survive without a hell lot of protection which we don't need. They are robust, and of course they are cheaper. So now you have a very specific competition. Something which is robust and cheaper on one side, and one is fragile and expensive on the other side. What will you choose?
Robust and cheaper.
Again, it will go down to the trade-off. How much advantage you are going to get. Less. If the advantage is very little, you are not going to waste your effort in it. You will only look for situation where there is a large advantage, which means again the problem dependence will automatically come in, and then you will do it. And so we have lots of devices, as I said, your laptops and mobile phones. They are working fine, they are doing its job. You are not going to throw them away. There is not going to be quantum mobile phone or quantum laptop or whatever it is. Not needed. We are already doing a good job with whatever which you have, and we are not going to get new advantage out of it. That is the whole point. If you are going to get some advantage, and not only small advantage, substantial advantage, then only you will invest in this highly fragile as well as expensive technology. Otherwise, you will not. And that is what you need to keep in mind. And now you can come back and look at the various questions like the one you asked. The theory is there, but does the problem have those particular features? And that is a different story. Superposition is there, it's there in all quantum dynamical phenomena. It's not a question of whether superposition exists or not, it's whether a question of whether you can make use of that superposition to get large quantum advantage or not. If you can do that, certainly you will opt for a quantum solution, but if you can't, then whatever you have is doing a good job anyway. So that is just to give a background, and the particular point of superposition, it is a property of any vector space. You are allowed to choose some basis, and in that basis you look at an arbitrary vector, it will have some components, and those components if you want to call it in the quantum Hilbert space, they are superposition states. While the basis states which you defined by your own convention are not superposed. But who decided the basis states?
Random.
I can choose a basis state in the sense that the vector I am looking at is along one of the axes. Then there is no superposition. Okay? So this is a point you need to keep in mind, that the superposition is not an absolute property. It's a relative property. And the question then is that, yes, you have the freedom to define this relative property, but can you get any advantage out of it? And that feature of superposition exists even in classical wave dynamics. You have electromagnetic waves of all these days, mobile phones floating around. What is the tower broadcasting? It's not broadcasting one message after another. It's broadcasting a superposition of all the messages. That doesn't make it quantum, and that doesn't. It actually is an advantage for the tower because it has to do one by one. That would be too much on effort. It's just doing it in one shot. So where is the caveat? The caveat is at the other end, the receptor. The receptor will have a particular device, and it can listen to one particular component of that message. Not everything. I cannot listen to everybody else's mobile communication. I will have my own device. I will pick out one particular component. And if that component has anything which is of use to me, yes, that is a good job. And it's not just mobile phone. This little bit older days, or even now, say radio broadcast or TV broadcast, you tune the channel, you pick up the one component which you want. Everything is there. It's up to you to choose one particular component. And then it becomes useful. So yes, superposition is available, but at the receiver end, the receiver is going to pick only one out of the many components. In quantum technology, that is the concept of measurement. When you perform a measurement, you will pick up one particular eigenstate. You can tune. Okay, you are allowed to adjust the basis so that whatever you want to observe aligns with that particular axis, and you can pick up that component. But the point is, you can pick up only one component. So if the problem is such that everything which you wanted can be nicely focused in that one particular component, yes, your job is done. If you can't focus it, it remains distributed all over the place, you are not going to get any advantage. So just having superposition is not enough. It helps that yes, you can have multiple possibilities all combined together, but together with the projection or the measurement at the end, which is generically present every time you have a superposition, you will have to find a problem in which you can focus all the information that you want in that one particular component. And the example which everybody nicely expected from Shor's algorithm is Fourier transform. So it basically says that if there is a periodic signal, then by doing a Fourier transform, you get a delta function. That has focusing into one component job. And that's why the algorithm has an advantage. The crucial point is, why could you focus it in one? Because the signal was periodic. If the signal did not have that property, there was nothing to be gained. And it is not the question of Shor discovered this nice property of Fourier transform. It's much older. People have used it even from the days of astronomers. Okay, so what do these high resolution images which you get from whatever stars, galaxies, every day, how do they manage to get that high resolution? You look at little bit of the physics involved inside that. There are two ideas buried in that. One is they use not just one telescope these days, but an array of telescopes. Distribute many sensors over different places, which allow them to do interferometry. And that interferometry picks out a certain advantage, which is useful, whether you call it classical or quantum is not really important, because ultimately it is a wave property. And they are using usual light, whatever it is. They don't have to go to a single photon level, but they can do interferometry with that, and that extracts some useful information. But there is other part also, that the observations which they make are also extended in time, not just in space. So what these telescopes, modern telescopes do is not just one snapshot of the sky. They do long time exposures, okay, over minutes and hours, focused on the same object. And how does that long time exposure help? They do a Fourier transform of that long time signal, pick out the delta function which is present in there, and get a high resolution. Okay, there is a lot of noise, but there is a signal, and the long time signal is cleverly picked out by doing the Fourier transform. So this is a nice property, it is a wave property, and it can be used in many different ways. The question is, you have to design your algorithm, making sure that the problem has certain kind of properties which will bring out these things nicely. So yeah, I think I have answered broadly in many things altogether.
Yeah, thank you. I got.
Hello, sir. My question is, can you throw some light on phase operator and challenges? Like phase is the important thing as far as quantum technology is concerned. So, like, why can't we define a phase operator, and what are the challenges defining it?
There is nothing like a phase operator. It is true that the quantum signals which we observe are fundamentally describing complex numbers. And complex numbers have two components in some language or the other. One of them is a magnitude and the other is the phase. And after that, it is your decision about what you want to focus on. You want to measure the magnitude, measure the magnitude. You want to measure the phase, measure the phase. Both are accessible. Various kind of instruments focus on one or the other. You can't do both simultaneously because of the so-called uncertainty principle, which is actually nothing but a property of a Fourier transform, that if you measure the intensity with high accuracy, the phase will not be measured with high accuracy and vice versa. But there is something which is called a quadrature measurement. You can measure both to a reasonable accuracy or one of them to high accuracy while giving up the other. So if you measure the magnitude, it is like measuring the intensity of the wave. That behaves more or less classically, or rather a classical language is used in that particular way. It's a magnitude, and you can label it with positive numbers with various types, and that can be very well represented with the Boolean algebra and all those kind of things which we do. And it is a so-called particle component of the complex number signal, And the phase is, in some sense, the wave component of the quantum signal. The full quantum dynamics will have both of them together, and you end up choosing what to extract in which particular circumstances. The standard method of extracting phase is various kind of interferometry. You can measure, again, relative phases in all the interferometry. There is no absolute value because you can rotate the coordinate axis whichever way you want, but you can measure interferometry and extract the values of various phases. If they are useful in your problem, well, you can focus on them. But there is no specific operator saying that I will measure the phase using this particular operator.
Can I just make a comment? I think phase operator is what it changes the complex signal. For example, you are talking about a complex signal. If you can change the phase by introducing any other frequency. So operator in the engineering terminology is something which changes the actual system. So if you have any signal, either single frequency or multiple frequency or whatever it is, if you introduce another frequency, that becomes an operator. It changes the system or changes the complex signal. And it changes the phase also. Phase and amplitude and the spectrum completely.
Yes, in quantum theory, operator is used in two different contexts. One is evolution, the other is observable. And they have different roles to play, and if you want to use the quantum dynamics properly, you should be able to distinguish what is the evolution and what is observable.
So you can have an operator which will change evolve the original system into some other system. So
Yes.
that is an operator in engineering terminology.
The quantum theory, those two operators belong to different classes. Evolution operators are unitary, the observable operators are arbitrary.
So we have been there has been so many development in quantum technology applications in applications which really have quantum advantages, but even in those applications the technology we have not been able to materialize it properly and implement it to our use. So why when and how will it happen?
It's a technological challenge. It is not a theoretical question about the mathematics. And the reason for that is quantum signals are highly fragile. You have to develop all the machinery to protect them. And that is actually a technological challenge. It is not a question of whether you have the right equations or not. And that is what makes it hard, and that is what makes it expensive. And you can't put a timeline on it that next year I will have this ready and 2 years after that I will have that ready. No. You have to actually do the hard work. A lot of it is engineering, but you have to do the hard work in the laboratory to be able to develop devices which are stable and which have a long-lived quantum signal.
So even after so much effort, the number of qubits which are actually needed to do something useful, we have not been able to get. So will it happen or
Well, people try. I mean, it's no guarantee that it will happen today or tomorrow, or whether with this particular machinery or that particular machinery, but people are trying. A lot of it is what you call trial and error. But unless you try, you will never find out. And sometimes it takes a new generation to bring out new ideas. It's buried in our, what you call, life system. Okay, I can go a little bit offline in a different direction. Have you seen children play with all kind of little blocks and things like that? They will make a house, they will make a car, they will make a doll, whatever it is. Does it matter to them how many other people have done this before? Or does it matter to them that what I will get out of it? No. It's an inherent curiosity, which everybody is sort of born with. And it's a fundamental aspect of life that kind of adventure, curiosity, is what leads to progress ultimately. And if you want to go into a research field, you have to maintain that curiosity. Not everything is going to work. Doesn't matter. That is not the goal. The enjoyment which the child gets is in the present, in playing, not the goal. And somehow the society destroys that. Child grows up a little bit, and then people ask the question, what are you going to be when you grow up? Satyanash. All the curiosity is destroyed. You are trying to straitjacket into some known direction, whatever the adventure or the curiosity is, and that's the way thing goes on. And what do the adults have which the child doesn't have? It's memory. They have, say, we have experience, we have done all those things, and this thing worked and this thing did not, and so we will not try this and we will try only something else. And what does nature do? Well, the memory is useful up to some extent, then after that you are old, now you go aside, let the new generation come and take up the challenge. So that is the story of life. Okay, it happens. And that is the way it has to grow. Yes, you have a knowledge, you have experience, it's useful up to some extent, but after that, you have to hand it over to the next generation who are willing to try without worrying about the consequences. And maybe something new will come out of it. We don't know. There is no guarantee. But that is the kind of attitude you need to be able to address new challenges. Without that, you won't get anywhere.
Hello, sir. So I'm Priyadarshini from. I'm an undergrad from Shastra University, and I'm a chemical engineer, a final year student. So basically, this workshop was a little overwhelming for me, for my level. Like it was more based on the computing and so. But the idea of quantum technology, I was really interested in that. That's why I came to the workshop. So I want to know: are there any areas as such that a chemical engineer can focus on in quantum technology, like areas that a chemical engineering can come into? So yeah.
There are lots of areas. You just have to look in your own subject. It's not limited to only the physicists or the mathematicians or the communication engineers or something like that. There are quantum phenomena in everything ultimately which is connected to dynamics at atomic and molecular physics. Okay, there will be lots of examples in chemistry where things are happening at the atomic and molecular level, and for which you don't have complete description. The reason for that is simple, that all the chemistry textbooks which are written, yes, they said that the quantum mechanics explained all those kind of things. Maybe they told you how this is how the hydrogen atom structure is, but then they reduce everything to classical language. And when they give that textbook description of chemistry, all the quantum physics is already taken out. They say that these are the atoms, they will make this kind of bonds, and you can count the number of electrons and do various kind of things. But that is an oversimplification. There's a lot of stuff buried inside. What is the structure of the bond? How are the electrons correlated? And there will be lots of properties of that particular type, which the textbook in chemistry will not explain. It's not that they cannot be observed. Certainly there are observations. But then you have to find those particular problems where the textbook description is insufficient, and you need to go a little bit beyond to understand things better, and you will find enough examples. I mean, chemistry is a somewhat simpler situation. Biology is a very bigger mystery. We know all the molecular dynamics processes of life. They are occurring at the atomic and molecular level. Do we understand any one of them? The answer is no. Things happen in every cell of our body. How are they happening? We don't know. We have some empirical rules, but they are not enough. And maybe if you understand the dynamics better, maybe you will be able to figure out more things. But like now, all the chemical industry or even pharmaceutical industry, they are all trial and error business. You want to study some reaction, you mix various things and stir it and see whether anything happens. That's all they can do. Do you understand what is the dynamics which is involved in the stirring and what is going to happen and what is good, what is bad, etc.? Those questions are not answered. So yes, there will be a lot of problems in many different fields where the underlying dynamics at the molecular level is not fully understood. You have to work a little harder to find such problems. But yes, if you find such problems, quantum physics or quantum technology will teach you something more about it.
Thank you.
Good question.
Hello, sir. Hope you're doing well. Well, I came from Agra to attend this workshop. And I'm in the last year. Like for past 2 years, I have been my undergraduate in cognitive science and physics. So when I heard about quantum computing and quantum physics, there's this branch of quantum physics that works in for the cognition sector of cognitive science. That's called quantum cognition. But then there are theories which are writing in that field, people are writing theories about it, that our brain, whenever our brain perceives something, it makes lots of possibilities in brain. And that's like comparing to quantum theories, it's like superposition of different thoughts, and then we say something, and that's like the collapse of the superposition state. So this is just trying to explain our brain using the quantum theory. But then again, we just cannot make theories without maths, without proving something. So I just wanted to ask you if you know if you know any way or any, mathematical terms or any calculations or equations or something that we can use to correlate the brain with the quantum phenomena. Because when we study brain, we go to neuroscience. But then again, there are very phenomena in our brain itself that we are not even doing classical physics or normal neuroscience. We need quantum phenomena in that also. But they are just theories. So I just wanted if you can elaborate on that or if you have any idea about that.
Well, first warning, everything you don't understand, don't try to blame it on quantum physics. There are a lot of things which are well known in terms of its classical origins, but we don't understand. That is a limitation of our own understanding. It's not just the question of that it is something which is mysterious. Okay, it's things which you need to keep in mind. Yes, it is true that computers from the beginning were modeled after repeating what is going on in the brain. Okay. They wanted to do first initially arithmetic, whatever addition, multiplication kind of stuff. It was well known in terms of algorithms, but yeah, if you give large numbers, it's too complicated. You give the job to a computer. Okay, it will do the calculation quickly and give you the answer. And nowadays, it's everybody's cell phone. You go to a market, the person will not try to make a bill with the addition. They will put it in the computer. Let the computer calculate the total, add the tax, whatever it is, and give you the number. That is fine. It is a certain amount of simplification, and well, our brain is capable of doing that. And the question was just that, do we want to burden our brain with that or not? If you can give the job to somewhere else, well, go ahead and do it. Then the whole system developed, and nowadays if you look at what goes inside the computer systems, does it do arithmetic all the time? And the answer is no. It hardly does any arithmetic at all. Most of the time it is shuffling data from one place to another. Either it is communications or document manipulation of various types of stuff. That's what we use our computers for. So it's no longer doing literal what the original computing meant in terms of arithmetic sense, but everything is now called computing. More generally, it is manipulating information in many different forms. So that is fine. And why are we doing that? Well, it was too boring to do that all stuff in our head, so we bypassed it, put it in the device to do that particular job. And yes, those kind of things always happen. We find good things to unburden our kind of drudgery. We do that. We develop a lot of instruments to do things easily, and computer has become those kind of instruments. It gives some advantages, etc. And we happily go along with it, no problem with that. But then the question is, brain also does many other things. And the continuous pursuit is, can we do all the things which the brain does and put it on the computer? Well, if you are literally doing that, then what is the purpose of your life? But that's a different question. People are trying to unload as many things on the devices from the brain. For what? So the brain can be used for something else. What that something else, nobody knows. But that is the game, and for that, well, you want to unload a specific task, you develop a model which will be good at handling that particular task, and that is what the industry has been doing, and it is completely okay. And in that sense, I can tell you that what we are developing are not a copy of the whole brain, but what can be best called a special purpose devices. They are good at doing specific jobs, and they are designed for that, to do it efficiently in some particular manner, and we use that. And even quantum technology or quantum devices which we are talking about, they will find their use as these special purpose devices. I already said that the problems which we will use it for are going to be problem dependent, or sorry, the devices will get advantage which will be problem dependent, and it is going to be expensive, and so you will use it only when you really get something good out of it, and that makes that it will make a special purpose devices. For some particular task it is good and you will use it, and for other tasks maybe the other systems are doing fine, maybe you will make a hybrid of this special purpose device with that special purpose device to do various kind of things. It can be part classical, part quantum, doesn't matter, as long as you can combine all those two together. So that is the story about what our brain supposedly does and what you are trying to mimic in the various kind of hardware that we are trying to make. But nobody has given a clear definition of what all things happen in the brain, or rather means more generally in even a living organism, which may not be something which has a brain. You can talk about bacteria. It also does lots of things. It doesn't have a brain, but it still manages various kind of things to the extent that it doesn't care about human culture or society. If you fall on the wrong side, the bacteria will kill you. So that is a kind of broad spectrum of what all kind of things happen in life, and what part of it you can extract and understand, and then you can make use of it. And certainly life is too complicated for us to claim that we have understood each and every part of it. We are too far away from any such a thing. We don't even know how does a bacteria do its own job. Okay, it's a tiny little thing, doesn't have too many components, not too many devices, but it still does lot of things which are completely mysterious. So yes, you can talk about all kind of words. What is consciousness? What is awareness? Or whether human beings are special or not in terms of some capability or not. All those questions really don't have a clean answer. And if you want to understand all this kind of question at a much simpler level, like a bacteria, if you are able to figure out something, that will be a great advantage before jumping on to saying that what our brain does.
Hi, sir. Sir, can we have your insights on quantum entanglement? Because all this technology depends on entanglement of single photon. Like that photon should be entangled for quantum technology. So can we have physics behind that quantum entanglement?
Quantum entanglement is nothing but a particular type of correlation. Okay. And it's not a separate property as it is hyped out all over the place in the media. It is just a simple consequence of having superposition and also having multiple components. If you have multiple components of a system and the availability of superposing their states, inevitably it will produce entanglement. It's a little trivial mathematical fact. You want to give it a different label and kind of exaggerate it as far as I'm concerned, yes, you can do that, but it's nothing but describing correlations that can exist in a multi-component system provided you have possibility of superposition. Nothing more than that in any mathematical description.
So, good afternoon. I'm George Paulson from Manipal Institute of Technology. I had asked this question in the first session yesterday regarding, so last October, in October of 2022, there were reports of 6 qubit chips that came out, and now it's in the June of 2023, it's 12 qubits. So is there a trend evolving just as with the Moore's law, just like that, or is it too early to make a call on it?
I think there was a quote from somebody, I don't remember the name of the person, and it goes something like that. It is quite hazardous to make predictions, especially about the future. We don't know. And that is a part of the adventure. Okay, if things were all perfectly predictable, then I can say there is nothing for me to do. It is going to happen anyway, so why I'm wasting time? And if it was completely unpredictable, then whatever I do is not going to contribute. I don't have to do anything either. The interesting part is that life is somewhere in between. It is not completely predictable and it's not completely unpredictable. And that is where everybody hopes to make some contribution. And yes, things change, but some things gradually improve, some things improve by accident. And I think Rohit mentioned some examples of this particular type, that in the last century, even after quantum physics came along, some things happened by accident, because people, you look at all the, what you call, science fiction, what all people were able to imagine with all the new technological development. They could talk about space travel, they could talk about aliens, and they could have, but did anybody predict atomic bomb? The answer is no. Even after quantum physics came along, there was no prediction of atomic bomb, but it happened. Did anybody predict the semiconductor revolution? Answer is no. Even after knowing all the quantum physics, it came essentially as an accident. And as Rohit mentioned, even after semiconductors came along, did anybody predict internet? The answer is no. And these things happened and they changed our lives. But not by prediction or some gradual improvement of something which already existed. So yes, both kind of things happen. Some things happen gradually, step by step, and something happen by jumps and bursts. You don't know what future has in store. Okay? So yes, you can say that some technology is going to improve. I have 5 qubits and I will make 10 qubits, etc. And whether that is a correct progression for the future, I don't know. Whether something which will be alternative will crop up from somewhere completely unknown direction, certainly not ruled out. And there is no conjecture about doing that. What you can do is work on the something which are called the foundational parameters or the fundamental principles of things, which gives you a broad platform on the strength of which you can try out various things. But you have to develop that first, a broad platform which is solid, and that is actually the purpose of education. Why does everybody learn all kind of things? You need studied history and science and languages, etc. in all our schools. Well, it's just to prepare that foundation. You are not going to pursue all those subjects in future, but it allows you to have certain kind of capabilities on basis of which you can try out whatever you desire to focus on. So yes, the qubits, the number will increase. How fast it will increase will depend on various kind of technologies may they be around. But the important point is to not focus on the qubits, but focus on the challenges which are already well known, like how do I make my qubit stable? That is a much more important problem than having a 5 qubit or a 10 qubit, because if the qubit is not stable, counting that number and making a hundreds and thousands of them is not going to help. So there are well-known technological challenges. Make a small device, but make it stable, make it well controlled, and if you are able to do that, it will have lots of applications, not just one application. Many different fields be able to use that kind of structure. The ideas which you obtain in the process of learning, because it's a question of design. It's not a question of applications. So the field of quantum technology, in my opinion, right now is a place where designing various things to the specifications that you want is a much more important task than counting the number of qubits. To give an example, look at our mobile phones. Okay? Of course, somebody made the hardware and made all the design and all the components that make work. But then the other end is a bunch of users. Do they know how the components work? Do they know even what is the basic principles involved in that? No, they will press some buttons on the graphical interface and it does the job, and that is fine. So where do you want to spend your energy? You want to develop this graphical interface where you say press some buttons and the job is done. Of course, it has some uses. People even who don't understand the machinery will use those apps and do some things which are of their use. Or do you want to spend the time where you design the system yourself? And both are important challenges in different domains. What happens in the so-called service industry is they are only looking at the user application side of the story. They are not looking at the design aspects at all. And most of the challenges of technology, the quantum technology, are in the design aspects. They are not on the application side. So if you learn how to design the systems properly, it can give you a lot of knowledge. Nowadays, this knowledge is there in specific pockets, but they are all protected. Companies have proprietary patents and all those kind of things about the designs they have developed, and they will not reveal it to the public, because that is where they make their money. But if you want to develop something and learn something in the process, you should be investing effort into learning how to design. And every device, quantum is just one example, but even classical device, that is how the industry has gone. They have so-called CAD tools, computer-aided design tools. And you will need similar tools for all the quantum devices as well. And somebody has to develop them. Okay, they are not going to be lying around in the open source domain for anybody to pick up. If you want to contribute to the technology and its future development, this is the place where investment can be made to develop the design tools. It is a useful area also in another sense that the effort and the infrastructure needed for developing the design tools is all classical. They will simulate the quantum systems, but the design tools will be still classical, and so you can invest in it with the existing resources which may be available in various places in various different forms. And that is one important area where there is a lot of progress to be made in quantum technology, because every device, as I said, it will be all problem dependent to some extent and special purpose devices to some extent, but it will need a good replica in the software before you go to fabrication. Because fabrication is going to be expensive, and that's why you want to make a nice design, so you know that there is a reasonably good chance of success. And that is an important area of technology development, which I think all the whatever government or industry or whoever is interested in the subject should promote.
Hello, sir. I'm Sri Hari and I'm pursuing my chemical engineering undergraduation. So, as we know, photosynthetic organisms such as plants and some bacteria have evolved for billions of years to such an efficient process called photosynthesis. So, and this high efficiency is because of one of the reasons because of this high efficiency is I read somewhere called quantum coherence. So my first question is what exactly quantum coherence is, and second question is what is your opinion on harnessing this understanding of quantum coherence in enhancing the efficiency of photovoltaic cells, whose efficiency is restricted to 30 to 35% right now?
Yeah, that is another biological problem which we haven't understood completely. And the plants solved it in some manner or the other billions of years back in some particular manner. It is true that the photosynthetic transport of energy is highly efficient. And our mimicry in terms of solar cells is not. And that is why the plant will absorb solar energy and make its sugars and glucose or whatever it does without getting heated up. And our solar panel tries to capture the energy, it becomes hot. That is because a lot of stuff is wasted. And all the wasted stuff is heat. So how do the plants manage to do it? Well, we haven't completely figured it out. Okay, but yes, there is important physics inside there. And yes, quantum dynamics is involved in some form or the other, mainly in terms of what is known as the efficient transport of energy. And how it occurs or how the parameters are tuned is something which we directly don't see. But what we have been able to observe, that there is a feature of wave dynamics in the transport. So the energy or the electrons which are carrying the energy, they are not flowing in a kind of down a gradient in a straight line fashion. They oscillate. And this wave signature is there. It can certainly help in the transport in the sense that the damping can be made much less. Because one standard model which people use for photosynthesis is that there is a gradient. So you will flow downhill in terms of this energy, one level being higher and energy at another level being lower, and you roll down. But if you really want to do that, then to maintain that energy difference, you have a battery. You need a battery. How are you going to maintain the energy difference? Plants don't have any battery. They do it irrespective of that. And that's what people study, and they figured out, no, there is no energy gradient which makes it go down. It's actually a wave-like transport. It goes all over the place and somehow it gets focused. It's not uncommon to have structures with focus waves. We use lenses all the time. No big deal. You can have an arrangement where multiple components of waves, if you have the correct geometry, the waves will focus in one particular place. And something like that is going on. We haven't figured out the full dynamics, but what the balance of energy shows that the transport is essentially some 99% efficient. Otherwise, the leaf would have gotten heated up. Doesn't happen. And yes, there are theories. Yes, there may be some quantum aspect of it, but nobody has figured it out completely. And it's an open challenge. Find out what literally goes on, and you have to work with real biological system, which is most of the time quite messy. Okay, it's not that easily isolated tabletop experiment where you can do whatever you want. Real system don't have that nice environment, and still the plant will do the job. Sometimes there are clouds, sometimes there are shadows falling from all over the place. It still has to do its work. It manages to do that. It's all various kind of mysteries which are buried in there. But yes, it's an open problem. People have recognized its importance, and they are studying it as well as they have made models of it, but the models are still not perfect. That's all I can tell you.
Thank you, sir.
Hello, sir. So I'm Sagar JC from NIT Surathkal, doing my master's in physics. So initially I was interested in theoretical high energy physics, and actually by many people they're like commenting that it is slowly narrowing field, and you don't have much opportunities in future, and it's very tough. But I see that you are interested also in high energy physics. So what can you like give a like suggestion to choose this field, like high energy physics, theoretical, or come into quantum computing?
You're asking like a reporter. That was not the purpose of this particular session. But yeah, all I can say is I studied various things and I made my choices. I was exposed to all kind of ideas. I decided to work on this topic versus that, and that has not remained constant as a function of time. For some time I worked on that because I found that interesting. For some other time I worked on something else because I found that interesting. And it's all right for everybody. Not necessary that you should be working on the same topic all your life. Your interests change, your motivation also changes, and if you find something which you enjoy doing, it's perfectly okay. And yeah, I worked on this because I was happy doing it. That's all I can say.
Sir. I have one question, sir. Like, what are the possible ways, like the advancement in quantum technology can contribute to our understanding of space science?
Space.
Because quantum is something that has always been dealt when we go for the space science and astrophysics and all those things. There is something about quantum that has always been happening over there. So how well these advancements in quantum technology can contribute to our understanding of space science, to unveiling the more and more about it? Are there any ways?
It's directly not relevant to space, but we can learn a lot about all kind of things which are around us in the whole universe. For example, one thing is by making sophisticated instruments. So one of the most sophisticated instruments is actually the observation techniques for gravitational waves. And those instruments now have gone into quantum domain. You detect gravitational waves, but you want to measure it more and more accurately. How do you do that? Well, you go to a stage where your instruments are detecting signals with quantum phenomena inherent inside the devices. They have reached that particular stage and they are putting it in. And they will allow us to make high precision measurements. You are using indirectly another system of that time, which is GPS. The signals are good enough. Well, they're not good enough, you want to improve them. You improve the resolution, you go to quantum domain. People are doing that. So Google Map will give you some resolution of 10 meters. You want to make 1 centimeter? It's possible. You have to go into quantum domain. People have already done prototypes of those kind of things in tabletop devices. They have not yet gone into putting them up into satellites or something like that. But yes, there are this kind of high precision instruments which will allow us to study all kinds of things, not necessarily atomic and molecular physics, but all over the space as well. No restriction on that. The other thing where quantum effects are important are in study of neutron stars and black holes, where we know the dynamics inside cannot be handled with classical physics. There is something more going on. Even in a neutron star, the density is so high that the quantum effects are necessarily going to play a role. Have we figured it out completely? The answer is no. But yes, the physics will have some use inside there to understand those kind of phenomena. Yet another area is the study of early universe, where universe was not so large, it was much more smaller in size, and certainly quantum effects are very important and played certain roles. The question is, are there any signals left from those early days which you can still observe? And people are very busy hunting for them. Okay? So these are quantum signals we are trying to pick out from the observation which we made, and they will tell us something not about the present universe, but the universe in those early days. And this knowledge, well, you can say, how does it affect our daily life? Maybe it doesn't, but it does satisfy some of our curiosity. And yes, there are applications of that type, yes.
Yeah, I think we can take one more question, after which we will end this session formally. And then if you have more doubts, you can approach us during the high tea or something, right? So one more question for this session.
My question is not related to quantum. Sir, actually my question is how important is PhD to pursue career in research? Is PhD really required to pursue career in research?
Well, I talked about it indirectly when I gave an example of how a child plays with all kinds of things. You try to fit yourself in some particular direction, maybe it will work, maybe it won't, but if you truly want to get into research, first make sure that you will be happy doing whatever you choose. It may not have the same status in terms of what your friends are doing and what the society is thinking of it, but if it's making you happy, that is a good criterion if you want to go into research. If you don't feel like that I'm not happy and this is not for me, you should not be in this particular field. Very clever or rather clear point of view. And yes, one thing I can also mention that lots of students come to me and they tell you, I'm very much interested in what you are doing. I want to work with you. Tell me anything you want to be done and I will do that for you. And my immediate response is, find somebody else. I'm not interested in somebody who comes and tells me I will do whatever you want me to do. See, the purpose of teaching, it's my own point of view, is not to give you the result. It is never the goal. The purpose, or rather the role of a good teacher, is to give you an idea about how to approach a problem. And that is what I also try to teach in my courses. Many times after the exam, students come to me, sir, I got the answer right, why didn't I get the marks? But getting the answer right was never the point. The point was, how did you arrive at that particular answer? The approach to the problem, the logic or the analysis which you use to think about that particular problem. That is the most important part in research. And if you are able to convey that, the job of the teacher is done. It's not to produce the final answer. It's just to put you in the correct direction. Yeah, that's a good point to end.
Thank you for such a great session. As a token of appreciation, I would like for Naipunya to give a little something to Professor Apoorva. So, yeah.